Hi, everyone. I'm Soos, and I'll be talking about hevm and symbolic execution that we built together with Lexi, myself, and Zoe. We're part of the Argo Collective. That is a recently spun out collective from the Ethereum Foundation. If you want a bit more about the Argo Collective, you can watch our talk that was given yesterday. So, first of all, what is this talk going to look like? So first, I'm going to talk a little bit about what it means to symbolically execute. Then I'm going to give a bit of an overview of hevm. Then I'll explain how hevm can be used within, to secure down some of your work that you have done, hopefully. And then finally, I'm going to conclude this talk. So first of all, what is symbolic execution? So let's say that your code looks like this. If you try to do fuzzing on this code, it will likely not find the fault that is marked by assert false, which could be, for example, something that drains your contract or locks your funds or some kind of negative event. So if you can keep fuzzing this forever, essentially, and nothing will happen. But if you run symbolic execution on this, it will immediately hit the assert false and will give you the solution, the two integers that you need to pass in to trigger the failure. So this is a good sort of litmus test of what symbolic execution can do in comparison to fuzzing. Of course, it can do more, but this is a good example where fuzzing will not help you very much, and symbolic execution will definitely help you. So let's get a little bit more into the details. So here we have, I used traditional assembly. I'm old school. I could have used EVM assembly, but it's more or less the same. So what we're going to do here is I'm going to showcase a very simple straight line program where we do a mov and a move and an add with two registers. So here we have concrete execution on the top, and what you have is concrete values like 1 and 2, and then the mov will move the value 2 to the A register, and then it will add 4 to this value, and then the final register state will be 6 and 2. Now, when it comes to symbolic execution, what it will do is it will, instead of initializing it with concrete values like 1 and 2, it will initialize it with a variable like v1 and v2, and then we'll try to execute these instructions, but over these variables rather than the concrete values. And what that will do is that, as you can see step by step, we have the state evolve, and eventually it will end up with v2 plus 4 on the A register and v2 on the B register. So, of course, if I substitute the concrete values into that, we'll end up exactly where we were with concrete execution. But what this means is that I can mathematically express what is the state for any input value, right? Okay, so that sounds interesting. Where does this get hard? Because this seems relatively straightforward. So it gets kind of hard is when branching happens. So here is a program where we have a branch. And with concrete execution, it's relatively straightforward. We have both registers set as 1. Then we're going to check whether they are equal. They happen to be equal. And if they are true, then we're going to add 5 to the register A. And so the final state is 6 and 1, right? So this is quite clear. But when it comes to symbolic execution, we don't know, of course, what the value of A and B is. We represent them as these symbolic variables, v1 and v2, and we need to check for both potential execution paths. In this case, when v1 is equal to v2 and when v1 is not equal to v2. And we'll end up with 2 different states potentially. In this case, we do actually end up in 2 different symbolic states. In one case, v1 is incremented by 5, and in the other case, v1 is incremented by 4. Of course, again, if I substitute the concrete values in, then I'll get exactly the concrete execution. However, what this means is that now we branch. So now we have 2 states, and if there's another branch, then this can become, of course, exponentially large number of potential end states. If there's a loop, of course, that can if it's infinite loop, it's not a bounded loop, then you can have issues with this thing never terminating because we don't actually know if ever the loop condition is reached, and so we can potentially run forever. So I'm just going to talk a little bit about what other symbolic execution systems are out there before I jump into hevm. First of all, there's more or less two types within this ecosystem as far as I understand. One of them is you have a static code analysis engine, and now you want to validate whether some of the things that it spits out are potentially false positives. And in this case, if the symbolic execution engine is not complete or doesn't understand everything, it's kind of fine, because what you will do is you will just simply spit out the potential false positive and let the user deal with it. And that's fine. But in our case, we actually don't use the static code analysis engine as a precursor to hevm, so we actually have to deal with everything that the EVM has to offer. So it's a bit more complicated, and it's also more complete, of course. So these purely symbolic execution framework-based systems, there are a number. There's Certora Prover, which is based on this backwards exploration and weakest precondition computation. There's ETHBMC, which is, of course, as the name suggests, a bounded model checker type system. Then there is Halmosh, it's written in Python, and then there's KEVM, which is based on the K framework and allows you to break out into K in case you need to prove some things, for example, loop termination or invariance and things like that. So just a bit of an overview of hevm. So it started a long time ago as part of the DAppTools project. It implements the EVM semantics both concretely and symbolically, and actually Echidna Fuzzer, if you know about it, it uses hevm underneath for the concrete execution semantics. It is possible to execute any call from any potential state in the EVM. So it understands a lot of, like, all of the EVM in terms of, like, for example, calling out to an RPC, to an archive node, to fetch state, etc. It basically computes a query to an SMT solver, runs the SMT solver to get the response to the query, and then interprets this response and sends it back to displays it back to the user in a fashion that is more user friendly than some SMT output. So we'll see that in a moment. So there are two ways of using hevm. One of them is for counterexample generation, and one of them is equivalence checking. So let's talk a little bit about this counterexample generation for, in this case, some kind of post condition that typically is written, for example, in forge test case, as a forge test case. So here we have Solidity, Viper, whatever language you prefer, or even just pure EVM bytecode, and that gets interpreted by the internal symbolic execution engine inside symbolic interpreter inside hevm to produce an intermediate representation. And then this intermediate representation, together with the post condition that you put down, gets compiled into a logical formula that gets sent out to the SMT solver. And SMT solver is what's called a submodal T resolver. So it understands, for example, bit vector arithmetic, which is quite useful because, of course, there's these 256-bit bit vectors or variables in EVM that EVM operates on. And then either it proves the property, finds a counterexample, or times out, of course. That's always a potential possibility. When it comes to symbolic execution for equivalence checking, we do something very similar, but what we do eventually is that we try to compare the two executions against each other. So you have bytecode A and bytecode B. Let's say that bytecode B is like a refactored bytecode or something that is gas optimized, and you want to make sure that it's doing the same thing as the original one. And now what this will do is that it will try to either prove that it is equivalent, find a counterexample, so some input or in state that where the two contracts actually disagree, or, of course, there's always the potential for timeout. And let's go a little bit deeper into this kind of symbolic execution engine inside hevm. So it operates on bytecode, which means that we're not tied to any particular compiler. We're not even tied to something like Yule, for example. Understands all of the EVM stack, call frame, stack, storage, call data, everything. As I mentioned, it can actually run at any point in the blockchain history. And it is fast against the concrete execution semantics of Geth in this case. As mentioned, like it has issues with loops and recursions because of this issue that unterminated loops, we don't know when to stop. It has some issues related to symbolic off-size and memory copy. This is purely due to SMT limitations and doesn't currently deal with symbolic gas, so it basically ignores gas when it comes to symbolic execution. In concrete execution, of course, it understands gas and will deal with it, and so Echidna will be running correctly in that sense. So just a bit of the internals. Maybe this is a little too small, but basically what it does is that it takes in as an input the EVM bytecode. Then it will step-by-step execute it and branch if necessary to build an intermediate representation. And then this intermediate representation is simplified in a generic way, and there are some specific simplifications related to Ketchuk and arrays and maps and things like that that are quite specific when it comes to how the EVM handles arrays and maps and things like that. So especially Ketchuk, which is very complicated to exactly represent in SMT. And eventually, what happens is that this IR gets compiled into a bunch of SMT queries, and these SMT queries get dispatched to the SMT solver or solvers. And then we gather all the results from the SMT solvers, and then get the counterexamples, extract them, and map them back to the query that was originally dispatched, and see how we can display that to the user in a way that they will be able to run this and actually trigger the fault. Because at the end of the day, it's annoying to get something like, hey, your problem is faulty. That's not going to help the user. But the user really wants some kind of counterexample so they can actually run it and see how it is wrong, and then of course they can fix it, or hopefully fix it. So that's kind of the high level of the internals. So let's talk a little bit about this intermediate representation. I'm not going to go into the details, but that's kind of at the middle of this whole box in the previous box that I showed. So here's a simple function, right? This will overflow if the variable that you put in is large enough, in particular exactly equal to 2 to the power of 256 minus 1. And B will actually not be larger than A in this particular case. I'm sure you have played around with this. It's a very trivial overflow issue. And this gets compiled into this intermediate representation where we have a proposition that A must be smaller than the A plus 1, right? So, I mean, it's very simplistic in this space, but the point was to make it kind of readable and also human readable. This can also be compiled into a graph, as you might imagine, and it can be quite understandable to a human how the internal representation maps back to the original code. In this case, it's quite clear. Okay, so I'm going to talk a little bit about how to actually run this tool and what kind of results you can expect. So in this particular case, we have a Forge standard test that we're going to import. Our contract is a test, and then we add prove underscore in front of it. You will need Forge, you will need Z3, which is one of the SMT solvers that we support, and you need hevm binary that you can just download from the repository. And you put down this test, and this test will, of course, fail, again, due to overflow. And the way you run it is very, very simple. You just build with the ESD and run hevm test, and it will parse everything up and do its magic, and eventually give you a counterexample, which is what you expect. So this is sort of the base way of using it. And it is as clean and tidy as it looks on the output. I did not actually change that or edit it, or didn't even the spacing is how it is. So it's quite visually representative of what are you going to test and what are the counterexamples that come out. If there's more than one counterexample, there's going to be more than one listed there. So how does hevm equivalence work? Here I'm just going to show sort of a contracted thing. It's a very complicated code that was someone tried to use. And here I just want to show some of the edge cases, but also that we do power through the edge cases as well. So in this case, there's 2 codes, and we want to know if they're equivalent. You see that it emits a warning that we cannot actually explore the whole thing in this particular case due to a call into unknown code. Obviously, we don't know what's going to happen there, like what is going to get executed. But beyond that, it says, okay, well, anyway, I powered through. Like, I'm going to ignore these bits and pieces. We have 1.7 million end states that we need to check for equivalence. And then it says, okay, well, I tried my very best. There's 93 of them I couldn't do because of this memory that was a memory copy that is symbolic. I couldn't do 2 because of timeout. This actually had a 15-second timeout for each query. And eventually, I couldn't find any discrepancies given these warnings and things that I couldn't actually explore. And if you have a look, this actually ran for like 34 minutes and 45,000 seconds. So obviously, it was like a multi-core machine that did this. So it doesn't like give up and like error exit or something like that. It actually gives you a meaningful output. And of course, this did actually check 1.7 million end states. So it didn't do nothing, even though of course you can't completely trust this because there are some parts that were not explored as displayed. Right, so I'm just going to give you a bit of a references and pro tips of how you might want to use hevm. So first of all, of course, there's the hevm repository. There's also a very extensive user guide. We have worked quite a bit on it lately, and it really does give a rundown, step-by-step, how to, the kind of outputs you can expect, etc. So it also explains, for example, some of these warnings that here are, of course, quite terse because we don't want to overwhelm the user with the output. Just a few pro tips regarding using hevm. So I would recommend, for example, using it for equivalence testing. The one that I showed you was specifically done by one of the compiler teams who wanted to check if their optimization or new idea actually doesn't break what the contract is expected to do, that the compiled contract is expected to do. So it's quite useful in case you want to refactor or if you want to do some gas optimized code, it can be useful. If you write a lot of tests, then eventually your tests are going to be your specification, and that can be quite nice as a driver for maybe thinking about your contract in terms of like what it's supposed to do rather than what the code says it's doing. And of course, I encourage you to do positive tests, negative tests, and invariant tests. For example, like a positive test is what we expect. For example, somebody types in, in a normal situation, not in this one, that positive test would be you type in the password and the password is correct and you're logged in. If you type in the wrong password, you're not logged in. An invariant in this case would be, for example, in the space of a blockchain would be that after transfer, the sum of balances is the same, right? And even if EVM, just a note, so even if hevm test gives you warnings and shows you that some of the things it couldn't do, it doesn't mean that it's useless in any way, shape, or form. You're not supposed to, like complete coverage is kind of a myth or something we want to get to, but it's very, very difficult. And what you normally get is a certain level of certainty, and hevm can help you improve this and elevate your level of assurance of your contract's correctness. And at the end of the day, that's what we're aiming for. Of course, it'd be very nice to have it all the way, but this is this I think is also very helpful, especially because it's more complete than just a fuzz test. So limitations, I think I've explained this before. So there's issues with loops, there is issues with recursion, and there are some issues with complicated mathematical expressions like exponentiation, modulo division, things like that, purely because it's complicated on a 256-bit variable. For future work, we're planning to help hopefully fix some of the issues regarding recursion and loops with some form of CHC. and potentially, hopefully, will help some better jump test handling, but also maybe EF will help with that. So in case you want to, there is, of course, the QR code, and check it out. Have a look, see what you can do. It should just work out of the box with your currently running tests.
Thank you. That was an excellent presentation. Can you come a bit forward?
Oh, yeah, sure.
Yeah. Okay, so let's start with the questions. Is hevm better than other tools such as Certora or Halmos in terms of compatibility with Foundry, easiness to use, etc.? So I guess it's a more DevX question.
Okay, I would not compare it necessarily to Certora. Certora has its own verification language. It's a multi-million-dollar company. It's a different ballgame altogether. But nevertheless, actually, hevm does very well, even though I would say from the perspective of what it's supposed to aim to do is slightly different, of course. We don't have a specific, not a specification language per se. We have these test cases which eventually become your specification. Regarding Halmos, I really like Halmos. So I think it's always fun to have more than one tool available for doing whatever you want to do. Not only because, if one of them doesn't work, then you can try the other, but also because the from a development perspective of the tool itself, of course, it's nice to see what Halmos is doing, and we copy something from them, and then they copy something from us, and that's what's called cross-pollination, and this is very normal in any field, including scientific fields. So compare, I don't know. I'm not a big fan of this kind of competition mindset. I think it's nice to coexist and work together, and I'd like to do that with both Certora and Halmos.
Yeah. So the next question is if we should avoid loops in code, or in more general, how can we write code in a more verification-friendly way?
Yeah, good question. Yes, no loops, please. In general, not a good idea to have unbounded loops because it can run forever. It will eat your gas. You can hardly reason about it from like what is it actually going to do. So I think it's not a great idea to have unbounded loops, and you should minimize the number of loops you have in general in your code. That also goes for recursion for the same reasons. You can, there are ways of like hevm can break out, and you can try to write some invariants and things like that. Hopefully we'll be able to do something like that maybe with including the loops into our IR, and maybe we'll be able to do something with that too. That'd be very fun and interesting. But in general, you're not only making our life harder, you're also making your own life harder. So perhaps avoiding it is the best way to go.
The next question is how do you deal with the path explosion problem?
We compile 1.7 million queries and run them in 34 minutes. That's the best way I can talk about it. Because
fair enough.
In the end of the day, it will happen, but you power through it. How does Certora do it? They have a farm of servers, and then 1.7 million queries get run in 5 minutes instead of 34 minutes. You can also do that with hevm. It's not a big deal. At one point, it's going to be pretty cheap to do that relative to how much money you're going to lose by not having it.
Mm-hmm. I guess the next three questions can be maybe answered in one go. So, is there any reason to use Z3 over CVC4, CVC5? Do you use multiple SMT solvers?
Yes. So actually, I don't know if it's publicly yet, but there will be very interesting tooling regarding, what is best from the Halmos team. I'm very excited for that. I personally, of course, am a big fan of Bitwood's Law and the team behind Bitwood's Law. I know them and I trust them and I like them. I also like Z3. If you know Nikolai, he's very good at what he's doing. So I'm still on the side of collaboration and friendly competition, and so anything works. As long as it works, I'm happy. So you can use actually any solver. You just do minus minus solver and do your own thing. You can also add your own if you like. You can even add the wrapper and then run any SMT solver instead of, you can even write your own. Like I think now even STP might work. Like I used to write STP, so although I was not very good at it, but I did also contribute to STP.
So I guess the last question, how hard are your KSAC constraints are on the solver?
We use the theory of uninterpreted functions to deal with Ketchak. That's the best way, I think, to deal with this particular issue. I'm not going to go into details because we're running out of time, but basically Ketchak is a very complicated function and representing it exactly is a very bad idea. So we, and I think many others, using the theory of uninterpreted functions to deal with it. It has some downsides and it can be problematic, but if you do a lot of rewrites on your maps and arrays, actually they can also completely go away. So with a good simplification routine and the best potential way of doing this kind of use of uninterpreted functions to deal with Ketchak, I think we can get there. It can be an issue, but I think with some luck and with perhaps even better rewrite rules, it's not such a big issue.
Great. Let's thank Mata one more time.